Within months, Typhoons were falling out of the sky, not from enemy action, but from their own catastrophic failures. Tails tore away in flight, engines seized without warning, pilots slumped unconscious at the controls, poisoned by carbon monoxide leaking into their cockpits. The Air Ministry considered halting production, while the RAF considered withdrawing the type. And yet German Armour would come to fear this same British fighter among the most dangerous Allied ground attack aircraft in Normandy. That reversal only makes sense when we stop treating the Hawker Typhoon as a failed fighter that was somehow rebuilt into a miracle weapon. It wasn't. Hawker corrected lethal structural faults, Napier made its Sabre engine more reliable, and the RAF redirected the surviving aircraft into the low-level war it was already unusually suited to fight. The Typhoon's actual achievement wasn't that it destroyed tanks at the astonishing rates claimed in 1944. Post-battle surveys showed that it didn't. Its achievement was making roads, columns, fuel lorries, artillery tractors, recovery vehicles, and exposed armoured formations dangerously vulnerable in daylight. It helped turn movement itself into a German liability. The aircraft had been designed by Sidney Cam's Hawker team to Air Ministry specification F-18/37, issued in March 1938. Britain wanted a fast interceptor to replace the Hurricane, a fighter capable of more than 400 miles an hour, carrying heavy armament and operating at medium and high altitude. Cam built the Typhoon around the Napier Sabre, an engine that promised almost absurd power for a British fighter of the period. The Sabre was a liquid-cooled, 24-cylinder H-configuration engine. Imagine two horizontally opposed engines stacked together, driving a common crankshaft. It displaced 36.7 litres, 2,240 cubic inches, and Sabre 2A tables gave it a military rating of 2,235 horsepower at 2,500 feet. That output gave the Typhoon immense low-level acceleration. It also created a machine that was heavy, complex, difficult to develop, and badly compromised for the high-altitude interceptor role the RAF had ordered. Less than 3 months later, on the 9th of May, test pilot Philip Lucas experienced a rear fuselage structural failure just behind his cockpit. Rather than abandon the prototype, Lucas landed it. The incident didn't reveal the full tail failure sequence that would later kill operational pilots, but it established an ominous fact before the aircraft had entered service. The rear fuselage needed close attention. First production Typhoons reached No. 56 Squadron in September 1941. Fighter Command began operational use in May 1942. The early aircraft had a dangerous combination of faults. Carbon monoxide leaked into the cockpit. The Sabre was temperamental. Structural failures appeared in the rear fuselage and tail. Pilots had to contend with these hazards before the Luftwaffe had fired a shot. Carbon monoxide was the first threat to become obvious. It didn't come from a mysterious internal defect inside the Sabre. Exhaust fumes entered through inadequate sealing and the early side-opening cockpit arrangement known as the car door. Typhoon R7592 crashed on the 1st of November 1941. Specialist studies attribute the loss to probable carbon monoxide poisoning. The RAF's response wasn't cosmetic. Longer exhaust stubs were introduced in November 1941. The port cockpit door was sealed. Pilots were instructed to use oxygen continuously unless the modification had been completed. Later Typhoon procedure required oxygen from engine start until engine shutdown. That detail changes the image of the cockpit. A pilot didn't simply strap in, start the engine, taxi, and take off. He had to use oxygen before leaving the ground because the aircraft's own exhaust system could poison him inside a closed cockpit. The engine created another layer of risk. Napier's Sabre didn't use conventional poppet valves. Instead, moving sleeves rotated and reciprocated around the cylinders, uncovering inlet and exhaust ports. The design had real advantages. It could breathe efficiently at high power and run at high revolutions. But it demanded precision manufacture on a wartime production scale. Napier's sleeves were made from chrome molybdenum steel. In mass production, their circularity could vary by a tiny amount. That sounds trivial until the sleeve must move inside a cylinder under enormous heat and load. A fractional distortion could cause rubbing. Rubbing damaged the oil film. Friction generated heat. Heat led to scuffing and seizure. The Institution of Mechanical Engineers summarized the problem bluntly. Mass production of the sleeves created circularity issues, which in turn had led to engine seizures. A Sabre seizure didn't offer a Typhoon pilot much time to think. The engine was liquid-cooled, the aircraft was heavy, and early operations often took place at low altitude. An engine failure could quickly become a forced landing, a crash, or a loss at sea. Accounts from the period report early Sabres being removed or overhauled after roughly 25 flying hours. Some frontline examples were reportedly down near 12 hours. The exact measure differs between sources: engine life, removal interval, or overhaul practice. But the larger truth is clear. Ground crews were servicing an engine whose available power was exceptional and whose early reliability was unacceptable. Cold weather made matters worse. Thick wartime oils could make starting difficult, and crews sometimes kept Sabres running or restarted them through the night so they would be ready in the morning. The engine wasn't inherently doomed by its H24 sleeve valve layout. Better sleeve manufacture, quality control, lubrication, balancing, ignition systems, and maintenance procedures gradually changed its record. But in 1941 and early 1942, the Sabre's power came with a punishing maintenance burden. Then the tail began to kill pilots. On 29th of July 1942, Typhoon R8633 of No. 257 Squadron crashed near High Urquhart in Shropshire. It had only about 5.5 flying hours. Its accident card was the first RAF record to explicitly identify structural failure. 2 weeks later, on 11th of August, Hawker experimental test pilot Kenneth Gordon Seth Smith took Typhoon IB R7692 up from Hawker's Langley Test Centre for straight and level speed testing. Seth Smith was 28 years old. He had been flying an aircraft whose defects Hawker was trying to understand and eliminate. R7692 broke up over Thorpe in Surrey. Witnesses reported a rising engine note, a loud report, and the Typhoon emerging from cloud in an inverted spin, while tail components fell separately. The visible result was horrifyingly simple. The tail had come away. The engineering explanation was more complicated. Investigators traced the failure sequence through the elevator mass balance system. A bell crank bracket failed. The elevator lost its mass balance. Severe flutter developed, rapid oscillation driven by aerodynamic forces. Vibration and loading, concentrated stress at the rear fuselage transport joint immediately ahead of the tailplane. The joint was where the aircraft separated, but it wasn't the entire origin of the problem. That distinction mattered because Hawker had to fix both the weak point and the chain that overloaded it. The company added tailplane strengthening. Modification 286 placed external reinforcing plates, fish plates, around the rear fuselage transport joint, backed by internal strengthening. Later changes revised the mass balance and control arrangements after Royal Aircraft Establishment resonance testing. Typhoons without the strengthening modification were progressively withdrawn between December 1942 and March 1943. This wasn't a total grounding of every aircraft in service. It was a targeted effort to remove the dangerous machines and rebuild them. Published totals differ, but the scale does not. Roughly 25 Typhoons and more than 20 pilots were lost to tail failures over the type's service life. Several histories report that during the Typhoon's first 9 months in operational service, more aircraft and pilots were lost to structural and engine failures than to enemy action. That is why calling the early Typhoon a death trap isn't empty language. It refers to a specific period of service when a pilot had reason to fear his engine, his cockpit air, and the structure behind his seat. Yet the same aircraft was doing something no other RAF fighter could do reliably. The Focke-Wulf FW-190 had begun low-level fighter-bomber attacks across southern England. These tip-and-run raids crossed the Channel at very low altitude, often below radar coverage, struck targets and raced back. Spitfires were formidable fighters, but in the conditions of these attacks, the Typhoon had an advantage: low-level speed. Typhoon patrols operated at 500 feet or lower. Its Sabre delivered strong power close to the ground. It accelerated hard and could catch low-flying FW-190 fighter bombers. By late 1942, sources described it as the only RAF fighter capable of reliably doing so. The reason it struggled at altitude was built into the original design. The Typhoon's wing used NACA 22 series airfoils. At the root, its thickness-to-chord ratio was 19.5%, tapering to about 12% at the tips. The wing was thick by contemporary fighter standards. It created drag, and at high speed it produced compressibility effects, buffeting and trim changes. Above roughly 20,000 feet, the Typhoon's climb, handling and combat usefulness were disappointing beside more specialized interceptors. The Sabre's two-speed, single-stage supercharger also lost effectiveness with height. At low level, the engine was brutally strong. Above 20,000 feet, that advantage declined sharply. But the wing had another side. It contained fuel tanks, 4 20mm Hispano cannon, ammunition, substantial structural members, and later the mounting points for bombs or rockets. Once the tail faults had been addressed, the Typhoon possessed load-carrying capacity, low-level speed, stable handling, and heavy fixed armament. Pilot Officer Simpson described it as quite easy to fly and very stable, a magnificent gun platform. That stability would matter far more against a road column than in a high-altitude dogfight. Roland B. Beaumont was one of the pilots who saw the aircraft's value before the institution had fully decided what to do with it. He had joined Hawker as a production test pilot in December 1941 after combat experience in hurricanes. He flew early Typhoons, worked on their vibration program, and understood their defects from both sides of the cockpit, as a test pilot and as a fighter pilot. Beaumont joined No. 56 Squadron in July 1942, then No. 609 Squadron in October. In January 1943, when Paul Ritchie left, Beaumont became the squadron's commanding officer. He didn't claim the Typhoon was safe when it wasn't. He argued that its basic design was sound once the known faults had been corrected. He emphasized its low-level speed, stable firing platform, maneuverability, and ability to carry punishment. Later, Beaumont recalled that people wanted to get rid of the Typhoon. His argument had operational evidence behind it. From Manston, No. 609 Squadron flew standing patrols against FW-190 raiders. Beaumont also began solo night intruder missions on 17th of November 1942, attacking trains on the Calais-Amiens-Paris line. By the end of December, 609 Squadron had reportedly attacked 25 trains. The Typhoon was already moving toward its future. No. 181 Squadron had begun using bomb-carrying Typhoons from September 1942. These aircraft became known as Bombfoons. Beaumont's train attacks showed that the machine could strike targets on the ground as well as chase raiders over the Channel. During the winter of 1942-43, Fighter Command, Hawker, operational squadrons and officers including Trafford Leigh-Mallory and Hugh Saunders debated the type's future. Beaumont was a leading advocate, not the lone saviour. There was no single, securely documented January conference that transformed the Typhoon overnight. The redirection happened progressively. Safety modifications reduced the aircraft's worst hazards. Sabre reliability improved. Squadrons proved the value of speed and firepower close to the ground. Bomb racks appeared. Rocket rails followed. The Typhoon didn't become useful because the RAF discovered a magical new aircraft hidden inside the old one. It became useful because the RAF finally assigned it a mission that rewarded what it already did well. By 1943, the Typhoon IB's basic punch was 4 wing-mounted 20mm Hispano cannon. The cannon were always there as the fixed armament. Bombs and rockets were mission loads. A bomb-carrying Typhoon could take 2 500-pound bombs, later 2 1,000-pound bombs. But the weapon that made the Typhoon famous was the RP-3. RP stood for rocket projectile. The designation said 3-inch, while the rocket motor itself was 3.25 inches in diameter. A standard rocket Typhoon carried 8, 4 rails beneath each wing. In northwest Europe, typical projectiles carried 60-pound warheads, including high-explosive and semi-armour piercing types. 8 rockets, 4 under each wing. A direct hit from a 60-pound semi-armour piercing projectile could destroy a tank. The conditional matters. The RP-3 was powerful. It wasn't precise. That distinction disappeared in much of the wartime legend because a Typhoon attack looked devastating. 8 rockets leaving the rails in sequence, cannon firing, bombs falling, dust and smoke rising from a road or orchard. An airman had seconds to observe the result while pulling away through flak. A burning truck, a detonating ammunition load, a tank crew abandoning a vehicle, or artillery striking the same target area could all appear to confirm a kill. By D-Day, Typhoon squadrons formed the main low-level fighter-bomber force of the RAF's 2nd Tactical Air Force. They flew armed reconnaissance, close support sorties, attacks on artillery, transport, rail movement, defended positions, road columns, and armoured formations. Some operated in cab rank systems, orbiting until ground controllers called them forward. Others hunted targets of opportunity or struck planned objectives. The method mattered because an armoured division wasn't just tanks. A panzer formation needed fuel bowsers, ammunition vehicles, workshops, recovery tractors, radio vehicles, bridging equipment, supply columns, and roads clear enough to use. Its tanks needed crews willing to remain inside them while aircraft attacked from low level. Its commanders needed to move in daylight, assemble forces, and recover damaged vehicles. Typhoons could disrupt every one of those requirements. Normandy's narrow roads, hedgerows, villages, and traffic bottlenecks made columns vulnerable. Allied air superiority made it difficult for German movements to conceal themselves once weather cleared. That pressure came from the wider Allied tactical air system, including RAF Typhoons, American fighter bombers, reconnaissance, attacks on railways and bridges, and the absence of an effective Luftwaffe response. The Typhoon's role was powerful precisely because it was part of that system, not because it fought alone. Operation Goodwood, from 18th to 21st of July 1944, showed both the legend and the problem. Allied reports claimed about 257 German tanks destroyed, including roughly 222 credited to Typhoon rockets. Operational research sections arrived after the battle and inspected wrecks. They counted 456 knocked-out German armoured fighting vehicles in the Goodwood area and examined about 301 closely. Physical evidence attributed only 10 of those AFV losses to Typhoon rockets. 10 wasn't a universal count of every tank hit during Goodwood. It was the result from the wrecks examined in that area, but it demonstrated the scale of overclaiming. A controlled trial made the problem even clearer. 4 Typhoons attacked a stationary Panther tank painted white, an ideal visible target, with 64 rockets over 2 passes. 3 rockets hit. That was a 4.69% hit rate. In combat, targets moved, hid among trees and buildings, threw up dust and fired back. A Typhoon pilot approached at high speed, released unguided projectiles and had little time to observe impact. Operational research commonly put rocket hit rates against armour at about 4%. A direct hit could be lethal. The chance of getting one was limited. This wasn't a failure of courage, it was physics, visibility, and battlefield confusion. At Mortain in August 1944, those limitations became impossible to ignore. On the 7th of August, German 47th Panzer Corps launched Operation Lüttich, a counter-offensive intended to strike west through Mortain toward Avranches and cut the American breakthrough. The attack involved panzer divisions, assault guns, infantry, and columns trying to move through ground already watched by Allied aircraft. RAF 2nd Tactical Air Force flew 294 Typhoon sorties against panzer divisions in the Mortain battle area. The US 9th Air Force also attacked. American infantry and artillery defended the ground. The German offensive was checked by combined arms, terrain, German command failures, fuel problems, Allied air superiority, and stubborn resistance around positions such as Hill 314. The air attack was a major part of that pressure, but it wasn't the entire victory. Wartime claims rose rapidly. Allied fighter bombers claimed roughly 252 tanks destroyed at Mortain, about 140 credited to 2nd Tactical Air Force and 112 to 9th Air Force. Post-battle survey work produced a different picture. About 177 German tanks and assault guns were involved. 46 were lost. 9 were attributed to air attack, 2 to bombs and 7 to rockets. That comparison, roughly 252 claims against 9 assessed direct air-caused armoured losses, isn't Typhoon claims versus Typhoon kills. It compares aggregate Allied claims with assessed air-caused losses. But it demolishes the image of aircraft casually erasing entire panzer divisions tank by tank. Why did claims rise so high? Multiple aircraft attacked the same vehicle. Crews abandoned vehicles under attack. A vehicle could burn after artillery fire, mechanical failure, demolition by its own crew, or a rocket strike. Smoke and dust concealed the real cause. Pilots couldn't stop beside the wrecks and inspect penetration holes. The operational research sections could identify direct destruction far better than they could measure panic, delay, dispersal, halted recovery, or vehicles left behind because their crews couldn't safely move them. That limitation isn't a loophole in the evidence, it's the key to understanding the Typhoon. At Mortain, a rocket didn't need to strike a tank to interfere with the counterattack. A column under repeated low-level attack had to scatter. Lorries carrying fuel or ammunition became exposed. Recovery crews couldn't calmly tow damaged armour off a road. Command vehicles and soft-skin transport were vulnerable to rockets, cannon, and bombs. A tank forced to halt, hide, or wait for supplies was still a tank removed from the planned attack. German daylight movement near the front became increasingly difficult because Allied aircraft could appear over roads, road junctions, staging areas, and supply routes. The precise effect varied with weather, location, camouflage, and the quality of Allied intelligence. Some German formations reached Normandy with fewer losses from aircraft than Allied propaganda later implied. Others suffered severe disruption. The important point is operational. Movement slowed, units dispersed, supply systems strained, and repair or recovery became harder. During the closing battle around Falaise and the retreat toward the Seine, that operational effect became visible across a much larger area. 83 Group claimed 141 tanks and 2,284 motor vehicles destroyed. Operational research later catalogued 5,644 German vehicles destroyed, damaged or abandoned in the Falaise-Seine area, including 358 tanks and self-propelled guns. That total does not mean Typhoon rockets destroyed all those vehicles. It includes damaged equipment, abandoned equipment, and vehicles affected by artillery, ground combat, mechanical breakdown, demolition, air attack, and the collapse of the German retreat. But an army retreating through a battlefield littered with thousands of disabled or abandoned vehicles had lost more than machinery. It had lost tempo. It had lost fuel distribution. It had lost its ability to repair and recover. It had lost control of the roads. That was the Typhoon's real battlefield function. Its 4 Hispano cannon were effective against soft-skinned vehicles, locomotives, gun positions, and troops in the open. Its rockets were terrifyingly destructive against transport and area targets, even when they missed tanks. Its bombs could strike concentrations and roads. Its low-level speed allowed it to arrive rapidly over targets. Its broad wing carried the stores. Its stable handling gave pilots a platform from which to fire. Its Sabre, once made manageable, supplied the power to lift a heavily armed aircraft and get it to the battlefield. The same thick wing that imposed drag at altitude held the fuel, cannon, ammunition, and load capacity needed for the fighter-bomber role. The Sabre demanded constant maintenance and engineering revision, while separate exhaust routing and cockpit sealing problems required strict oxygen discipline. Together, these changes gave the Typhoon its violent, low-altitude performance. The same large, heavily built airframe that had been unsuited to high-altitude interception could absorb the loads of low-level attack after its structural defects were corrected. It wasn't a wonder weapon. It was a machine whose original mission had concealed its actual value. That distinction also explains why a simple comparison with the American P-47 Thunderbolt misses the point. The P-47 operated in different organizational and technical circumstances, carried heavy ordnance, and benefited from a radial engine rather than the Typhoon's vulnerable liquid cooling system. The Typhoon wasn't universally superior to every Allied fighter bomber. Its importance came from how RAF 2nd Tactical Air Force used it over northwest Europe. A fast, heavily armed, low-level strike aircraft integrated into a tactical air system built to attack an army in motion. Pilots still paid heavily for that role. Even after the tail modifications and engine improvements, Typhoon crews flew into intense light flak at low altitude. The aircraft's radiator and cooling system remained vulnerable to ground fire. A successful rocket run often meant descending toward a defended column, firing or releasing weapons, then pulling away through rifle fire, machine gun fire, cannon fire, and fragments. The Typhoon's redemption never erased the men killed during its early failures, or the pilots lost later attacking the German army at treetop height. By 1944, the aircraft that had frightened its own squadrons in 1942 had become indispensable to the Allied ground campaign. But the reason was colder and more precise than the old tankbuster legend. A rocket Typhoon didn't have to score a direct hit on a Panther or Tiger to matter. It could force a road column apart. It could destroy the lorries that carried fuel and ammunition. It could kill the vehicles that pulled artillery, recovered tanks, and maintained communications. It could turn a daylight move into a halt beneath trees, in ditches, beside burning transport, while American artillery and infantry closed in. The Typhoon wasn't saved by becoming a sniper in the sky. It was saved because the RAF found the war in which its existing strengths, thick wing, heavy guns, enormous low-level power and load capacity were exactly what an attack aircraft needed. And across Normandy, the evidence points to the consequence German armour couldn't afford. Not every tank destroyed, but an armoured force increasingly unable to move.